All right, let's dive right into this explainer and channel our inner detective. I want you to picture that classic nightmare scenario. You're working in a fast-paced lab, the centrifuges are spinning, the chromatography screens are humming along, and you've just finished running a really crucial sample. You're waiting for the sequence to finish, and suddenly, bam! A flashing red fail pops up on your monitor. Your result is outside the specification. In the high-stakes world of pharmaceutical manufacturing, you've just hit an OOS, an out-of-specification result. So the second that alert flashes, we are instantly faced with a high-stakes mystery. Is this a genuine product failure, or is it just some weird fluke in the lab? We can't just guess here, right? Lives could literally depend on the medication we're testing, and the financial implications for the company are, well, massive. We need a highly methodical, airtight process to figure out exactly what went wrong. To solve this, we're going to map out our forensic audit. First, the anatomy of an OOS. Second, a Phase 1B deep dive. Third, a Phase 2 manufacturing review. Fourth, a real-world case study. And finally, the FDA red flags. Section 1. Anatomy of an OOS. Phase 1A. The golden rule. Okay, stop right there. Before you even think about touching that beaker or rerunning that test, you gotta remember, the FDA's ticking clock, it just started. They expect a timely, thorough, and totally documented investigation. Because of this, we always start with the rapid-fire duh moments. These are the quick, immediate checks to see if the mistake is just staring us right in the face. First, check the math. Did you simply move a decimal point by accident? Second, check the equipment. Is the HPLC column leaking? Third, check the sample prep. Did the solution turn cloudy when it was supposed to be crystal clear? We do this because if we find a super obvious error right here in Phase 1A, we document it, we invalidate the initial result, and we retest. Boom, saves everyone a massive amount of time. Moving on to Section 2, Phase 1B, the deep dive, the forensic audit. But you know what happens if you check the math, the equipment, the prep, and everything is actually perfect? If there's absolutely no smoking gun from Phase 1A, we can't exactly just shrug and walk away. We are forced to launch a formal forensic audit to uncover the root cause, typically using the 6M's framework. We literally interrogate every single lab variable by systematically eliminating suspects. First, man, was the analyst actually trained properly? Second, machine, is the instrument fully calibrated? Third, methods, is the standard operating procedure totally ambiguous? Fourth, materials, were your reagents expired? Fifth, Mother Nature, was the lab humidity way too high for a sensitive powder? And finally, measurement, was the standard concentration even correct to begin with? We have to ruthlessly check every single one of these boxes. Section 3, Phase 2, Manufacturing Review, Crossing the Threshold. Now, imagine we finish Phase 1B and it turns up absolutely nothing. The lab did everything flawlessly. At this point, the investigation crosses the threshold, leaving the microscopic lab and stepping right onto the massive factory floor. Here, we're scouring the batch's birth for hiccups. We're looking for any tiny deviation in how the product was actually made. We scrutinize the batch records, we hunt for equipment malfunctions like did it heat or suddenly spike for 10 minutes, and we profile any personnel changes, like a shift change or maybe a brand new operator stepping onto the line. We are trying to find the actual manufacturing root cause of our OOS. During this Phase 2 process, we might need to do some hypothesis testing to see if a suspected error, like inadequate mixing, can actually be proven. And this brings up an absolutely crucial distinction you need to understand: retesting versus resampling. Retesting uses the exact same original sample you already pulled. Resampling, that means grabbing a totally new sample directly from the batch. And listen closely, you only ever resample if you can explicitly prove the original sample was somehow compromised. Otherwise, it kind of looks like you're just fishing around for a good result. Section 4. Case Study. The Floating Assay. Real-world detective work. Let's actually put this into practice because it perfectly highlights how Phase 1 and Phase 2 work together to solve a genuine mystery. Just imagine the absolute shock in the lab when the assay for a pharmaceutical tablet comes back at a dismal 82%. I mean, the acceptable limit is strictly 95 to 105%. So an 82% result isn't just a tiny miss. It is a massive glaring alarm bell that something is fundamentally wrong with that medication. Let's trace our detectives on the timeline here. Hour 1, bam, they identify that 82% result. By hour 24, the Phase 1 lab check clears entirely. Fresh reagents, stable machines, zero lab errors. So they escalate to Phase 2. And by hour 48, Out on the manufacturing floor, they discover that the specific blender used for the powder mix had a dead spot where the powder just wasn't mixing. Because of this amazing detective work, by hour 72, the verdict is in. The OOS was valid, the batch was completely non-homogeneous, and it was rightfully rejected before it could ever reach a patient. And of course, the blender was then modified to fix the issue. Which brings us to Section 5, FDA red flags and CAPA, the law. Ultimately, guys, all this detective work brings us straight to the law. Because the FDA doesn't just care what you found, they heavily scrutinize exactly how you investigated. There are these top FDA 43 observations, basically their formal warning notices, that highlight massive red flags you absolutely must avoid. First, testing into compliance. No, you cannot just test a sample over and over until you finally get a pass and magically ignore the fails. Second, averaging OSUs. You can't just average a failing 50% and a passing 100% to get a passing 75. That is straight-up data manipulation. Third, lack of timeliness. Letting an investigation sit for 60-plus days without a really good justification is totally unacceptable. And finally, my favorite, defaulting to analyst error. Lazily blaming the human without rock-solid proof just to avoid throwing out a batch is a fast track to serious regulatory action. If you remember absolutely nothing else from this explainer, remember this. An out-of-specification result is never a failure. It's a data point, right? It is this incredibly vital piece of evidence that, when investigated with a robust process, protects both the end patient taking the medication and the company making it. As we wrap things up here, I really want you to internalize this exact flow. You identify the issue, you investigate the lab in phase 1, you investigate manufacturing in phase 2, you find the root cause, and you implement a CAPA, a corrective and preventative action. Seriously, don't fear the OOS. Fear a lazy investigation. So, looking at your own lab's daily processes, I'll leave you with this question. Are you genuinely investigating to find the truth, or are you just trying to pass a test?